Okay, so I'm excited to kick off this podium session and to share a little bit about our work on simulating adaptive treadmill gait. So first off, why did we decide to simulate treadmill gait in the first place? Treadmill gait training is a commonly prescribed intervention for individuals post-stroke, as it's been shown to improve walking function, efficiency, and increase walking speed. Treadmill gait training is typically conducted at fast speeds, because as you can see here, there's a clear correlation between propulsion and walking speed, and one of the primary goals is to improve propulsion on the paretic side. However, only about 50% of individuals post-stroke actually respond to regular fixed speed treadmill interventions that are commonly prescribed, and one possible reason for that is because it restricts the natural variability between strides that you see in overground walking. So to address this concern, we developed an adaptive treadmill that changes speed in real time based off of changes in user step length, propulsive impulse, and anterior posterior position on the treadmill. So if you take larger steps, push off harder or longer, and move forward on the treadmill, the belt will speed up, vice versa, it'll slow down. We're really excited about this as a tool for post-stroke intervention because we've seen young healthy adults choose faster self-selected walking speeds and push off harder on the adaptive treadmill than we have fixed speed treadmill. So we think it's a good tool for rehabilitation, but as you can see here, when we tested this with individuals post-stroke, with a set of 20 individuals, 14 of them increased their speed, but 6 of them decreased their speed on the adaptive treadmill from the fixed speed treadmill by roughly the same magnitude. So that led us to our next question. How can we further customize the adaptive treadmill to promote desired outcomes for everyone? So we started with some experimental trial and error with 21 young healthy adults walking on what we call our different modifications of the adaptive treadmill. For these modifications, we changed the values of the gains on each of these terms, alpha, gamma, and beta, to try to really emphasize those terms and the importance of those terms on the overall belt speed. So we had 10 different trials, equal condition where the gain on step length and propulsive impulse were equivalent, 3 conditions where we increased the gain on step length, alpha, and 3 conditions where we increased the gain on propulsion impulse, gamma, and then some conditions for position. As you can see here, we're really excited that we were able to, with these modifications, increase from left to right. We increased that value of gamma. We were able to promote greater propulsion. But this required 10 different trials for individuals at least. We could have done more with adding more modifications. And individuals post-stroke, we can't ask them to walk on the treadmill for this many different trials. So this is where computational simulation comes in for us. And the goal of our work was to develop and evaluate a predictive simulation framework to estimate changes in gait patterns with various adaptive treadmill designs so that we didn't have to have these individuals post-stroke or individuals complete this many trials. So for starters, we use a 2-dimensional OpenSim treadmill gait model with 9 muscles on each leg and 2 contact spheres on each foot. We started by simulating a fixed speed treadmill. So we prescribed the motion of the belt that we added into this model. And for the adaptive treadmill simulations, we've since modified the belt speed to become a free parameter that is chosen by the simulation. Our simulations were run using direct collocation optimal control methods in OpenSim Moco. We started with inputting the model into a tracking simulation to get an initial guess for our predictive simulation. And the tracking simulation minimized the controls, U, as well as an error between reference and simulated states, E-track. And we had the constraint of bilateral symmetry to allow for quicker convergence times. Like I said, the tracking simulation solution was the input into the predictive problem where we minimized the controls, again, U. We minimized an error between simulated and reference belt speed, EV belt, multiplied by a constant, so that the error keeps the speed constant, but the constant that we're multiplying allows for scaling of the magnitude of the speed. Then the other 2 terms are to maximize step length and propulsive impulse. Our constraints here were bilateral symmetry again, as well as 0 velocity of the center of mass of the model relative to the ground, so that we didn't have slipping between the contact spheres and the belt. Then we modified, similar to how we had done it experimentally, the values for the weights on step length and the propulsive impulse terms to simulate 5 different controllers. So let's get into the results. As you can see here, this is our simulated or predicted step lengths for the 3 conditions: equal, low step length, and high step length. And from left to right, we increased that value of WSL. As you can see, there's not a clear effect of increasing that value on the result of the step length as we go down in step length and then we go up. Also, the changes are relatively small and similar to variability that you'd see between steps for healthy young adults walking over ground. So talking about change in step length, this is what we're really excited about. We're comparing here our experimental data of 21 young healthy adults walking on the adaptive treadmill in similar conditions. Those are the bars, and then you can see the X's represent what we were able to predict as the change scores in step length between those different conditions of the belt. And as you can see, our predicted values match the experimental values. So we were able to predict the trends or lack thereof in changes in step length that we observed experimentally. Propulsive impulse, I'll present in the same way. From left to right, we increase the value of WPI. And here you actually see that increase that we were able to predict with increase in propulsive impulse with increase on that weight. And again, really exciting, we were able to simulate what we observed experimentally with increasing propulsive impulse with the increased weight on that propulsive impulse term in the adaptive treadmill. So it worked. And then finally, real quick for the results, all of our simulation convergence times were under 10 minutes. We're really excited about. I know it's a 2D simplistic model, so that could be part of it, and it could increase if you made the model more complex, but 10 minutes as a starting point is pretty great. So our key takeaways here are that overall, we were able to create a simulation that predicts customized responses to the adaptive treadmill, similar to what we observed experimentally. As we increased that weight on propulsive impulse, we were able to predict and observe experimentally an increased propulsive impulse from the user, and there was no clear trend in how step length changed with increasing that weight. And we hope that we can use this now as a tool to further understand the biomechanics of gait on adaptive treadmill and its variations, and to be able to kind of understand who may respond best to which versions of the adaptive treadmill. So our future directions, we've kind of already started it, but we're working on simulating hemiparetic adaptive treadmill gait on these different modifications as well, so we can get a good initial guess of how these individuals may respond to these different variations of the adaptive treadmill, and maybe further improve the design of the adaptive treadmill for individuals with a variety of impairments, as well as a variety of therapeutic goals. So finally, the NSF discussion points. The first question is, what challenge are we addressing using computational modeling? So as has been discussed a lot here, with these different patient populations, there's a lot of heterogeneity and differences between individuals. So it is really difficult to determine who will benefit from which version of an intervention, as well as how to change an intervention to be best for an individual. And so we hope that this kind of predictive simulation framework will allow us to address that question for adaptive treadmill control designs. The second question we broke up in two: how has modeling supported our work, and how could we use it to enhance our work in the future? In terms of support, we have noticed a pretty large psychology effect with individuals walking on the adaptive treadmill. And so this allows us to kind of deduce a cause and effect of changes of the adaptive treadmill on the resulting gait mechanics without taking in some of those components that we can't take out experimentally. And then how it could enhance the work in the future. We haven't done much with learning, but a lot of you have, as we've discussed the last day and a half. So we'd really like to be able to model and predict how individuals will learn and how those learned behaviors will be retained over ground with these different changes with the adaptive treadmill. And then finally, a key opportunity that we see here, this work was just with simulating adaptive treadmill gait, but we'd really like to see similar predictive frameworks developed for other rehab interventions like robotic training or exercise or what have you, so that we could essentially understand which version of these interventions would be best for an individual, but also what intervention might be best for an individual as well. At this point, I'd like to acknowledge our funding sources, as well as my collaborator, Dr. Nick Bianco from the WUSI Human Performance Alliance, and all of my lab mates. And I will take any questions.
Thanks for the nice talk. I was also excited to hear that it worked. So my question was about other things working, I guess. So do you see other changes in the kinematics when the participants are walking on the adaptive treadmill in other aspects of joint angles or center of mass movement? And did you see those similar changes in the simulations?
So I just got these predictive simulations working last Saturday. That's why I said it worked very enthusiastically. So we haven't had a ton of time to dig into the kinematics. Experimentally, we didn't see a ton of change with the kinematics. So I'm not sure if we'll be able to predict that. Another cool thing that we were able to show was, since the belt speed was a free parameter, I didn't talk about that here. But in our experiments with the increase in propulsive impulse gain, it essentially created a resistive training environment. So even though they increased propulsive impulse, they didn't increase speed, and our simulations predicted that. The other thing we saw was they increased stance time instead of increasing peak propulsion, and our simulation predicted that too. So we're pretty excited about how much it matched the experimental data overall.
Excited to see more. As
Thank
you
you.
have time to actually look at the results.
Yes, thank you.
And I like the late breaking nature.
Have time for more questions.
So Kayla, great talk. So I'm interested in your thoughts about the potential effect or impact of sensory impairments on the variability that you presented at the beginning. And if you have any ideas about how, or if you could integrate information about sensory impairments in this computational framework.
Yeah, so for our hemiparetic simulations, we would really like to be able to personalize them to individuals. We haven't quite gotten there. So our goal is essentially to decrease the maximum isometric strength on one side and predict the resulting gait. Again, I haven't had much time to look into those results. That's what I'm hopefully going to be doing for ASB this summer. It's a quick plug, but that's definitely something we want to look into with those simulations for sure. I just haven't had the time to get started on that.